right, so we're going to start talking about something called intermolecular forces. And you will see me abbreviate intermolecular forces just with an IM, right? It's too big of a word for me to write out that often. Right? I don't got time for that. So IM means intermolecular forces. Now, we have got to I want you to first start thinking about the difference in the prefix inter and intra. Do we know the difference between those things? The difference between inter and intra. Yes or no? I'm seeing a lot of no's. Okay. There is a difference, inter and intra. Okay? Intra means within. So within something. Inter means between two things. Okay? So if we know that inter means between two different things, right? Think about the interstate. It goes between a lot of different states. Okay? But infrastructure of something, right? That kind of means within that system's own insides, kind of. Okay? But intermolecular forces, if that means between rather than within, that means intermolecular forces are the forces of attraction that happen between molecules. They're not the things that happen within molecules. Okay, so tell me, what are the types of forces that hold molecules together within themselves? Do you know? What is it that holds the two individual atoms together? You're overthinking this. We've been doing it the whole chapter. Bonds, right? Bonds are what hold atoms together. So a bond would be considered an intramolecular force. And then intermolecular forces are a different set of those. Okay? If I'm just going to ask you right before we even really start studying this, which type of force do you think is stronger? An intramolecular force like bonds or an intermolecular force? Intra, right? It's easier to split two molecules apart than it is to split an individual molecule into its atoms. Right? Does that make sense? It's easier to separate two molecules than to break one molecule apart. Okay, so we're going to have kind of a scale of strength of forces or strength of attractions. And these intermolecular forces will be on the lower end of that spectrum. Right? They're not super strong. But we're going to talk about what the differences are. So I want to think about phase changes to help us identify or understand intermolecular forces. Okay, so you don't necessarily have to write this part down 100%, but I want you to start thinking about it. If I have to melt something, melting is going from what physical state to what physical state?
Solid to liquid.
It goes solid to liquid, okay? And when I do that, a particle in a solid state, those atoms and those molecules have to be held together by something, right? Solid state particles have to be held together by something. They don't stop moving, right? Particles in a solid are still vibrating, still moving a little bit, but they're being held together in that rigid state. So what is it that's holding them together, right? That is what we would consider an intermolecular force, okay? So when we're in that solid state, we need something to break it down, and that usually comes in the form of heat, right? Because when I go from a solid to a liquid, what has to have happened to the temperature? Right? It goes up. I should have asked that question the other way around. If I heat up a solid, what happens? It melts. It goes to a liquid, right? Some substances take a lot more heat to melt, and some substances don't take very much at all. Okay, and that has to deal with the types of forces they have holding them together. So the higher that the melting point or boiling point of a compound is, that means it has stronger intermolecular forces, right? It's hard to break those molecules apart. So we're going to start looking at what types of compounds have what types of intermolecular forces, and we'll be able to know a little bit about those different forces. Anybody have their book with them? Yes, no, that's all right. I don't usually need you to bring it. On page 204, it has kind of a list of boiling points. So I want to walk through or mention a couple of these. Okay, you don't have to have your book. I know we don't ever hardly use it. All right. So let's talk first about a substance we know and its boiling point. Okay? Does anyone know the boiling point of water? What is it for water? In Celsius. 100. Okay. So in Celsius, water has 100-degree boiling point. I'm going to look now at a different type of a molecule, H2. H2. So what is H2? It's two hydrogen atoms bonded together, right? And is H2 usually a solid, a liquid, or a gas?
Yes.
A gas, right? It would be very, very rare that it would be a solid. Okay? The boiling point to make hydrogen a gas is negative 253. Right? That's when it becomes a gas. This is Celsius, all Celsius. Okay? So it's got a really, really, really low boiling point. It becomes a gas really easily. Really, really easily. Let's go on the other side of that. If I was looking at just copper, the metal copper, would you expect a low boiling point or a high boiling point? A really high boiling point, right? It takes a lot for metal to come to a boil, right? To become coming to a boil. So the boiling point for copper is 2,567 degrees Celsius. Right? We see the difference in those types of boiling points. There are really, really, really strong intermolecular forces between metals. Pretty strong intermolecular forces in water, but really, really weak intermolecular forces in hydrogen gas. Does that kind of make sense? H holds on to the other H really tightly, but it does not hold on to the next molecule. Okay? Water holds on to its oxygen and hydrogen pretty tightly, but it doesn't hold on to the next water molecule that tightly. But copper clings to its whole self. Right? It wants to stay together in a solid. Okay? Or at least at this point in a liquid, right? That's its boiling point, not its melting. Questions with that? I just want you to see the relationships of how those move. All right, the first intermolecular force we're going to talk about is something called hydrogen bonding. Hydrogen bonding. Now, the kind of caveat to this term hydrogen bond is that it's not really a bond, right? Because what has to happen in a bond? Tell me the two types of things that might happen in a bond with the electrons. They're shared or they're traded or give and take, right? That has to happen. There's got to be an electron movement for us to be considered a bond. So hydrogen bond is called a bond, but it's really not, right? It's like an imposter, okay? Hydrogen bond is an attraction. It's just an attraction between a hydrogen atom of one molecule and a partially charged atom of a different molecule. Okay? It's just an attraction. I also want you to put right here by hydrogen bonding that it is our strongest intermolecular force. Okay, we're going to look at kind of a strongest and a weakest. Hydrogen bonding is the strongest type of intermolecular force we will see. Okay, it says it's an attraction between the hydrogen of one molecule and the partially charged atom of a different molecule. So in order for in order for molecules to have hydrogen bonding, what's the one atom they have to have? If my substance is going to have hydrogen bonding taking place, what atom has to be present? Has to be hydrogen, right? I cannot have hydrogen bonding if my molecules don't have hydrogen in them. Agreed? Right, got to have hydrogen there. Okay? So, like we said, this is not truly a bond. It's an attraction. It's a pretty strong attraction, but there is no trading or sharing of electrons happening, right? It's just an attraction. It's just a positive, negative attracting to one another, right? We've talked about that, right? Positive and negative will pull closer together and be an attraction. Okay? We usually represent a hydrogen bond by a dotted line, whereas a true bond is represented with a solid line, right? A dotted line here represents a hydrogen bond like we see down here. And the covalent bonds is represented with a full solid line. Okay? There's a difference there. So I want to walk through this diagram right here. Can everyone see that diagram, or do I need to make it bigger? Let me zoom in. All right, I want to take a look at this diagram here really quickly. We talked in terms of polarity, about polarity within bonds, right? Do you remember between hydrogen and oxygen, which is more electronegative? Oxygen, right? So if I'm looking at dipole moments here, oxygen's more electronegative, which means oxygen takes on a what? Partial what? Partial negative and a partial negative, right? From each of these bonds. So this oxygen has two partial negatives right here. These hydrogens have a partial positive, and doesn't the same thing happen on that other water molecule? Okay, partial negative. So now, what do we see happening with this hydrogen bond? Yeah, right. You see this partial negative here is attracting that partial positive, and it's enough to hold them closely together. So that means if I had another water molecule, right, I would see a partial positive. I would see another hydrogen bond happening here. I would see another hydrogen bond happening here, right? When water molecules are in proximity, that attraction will happen just by the attraction between the partial negative, partial positive. Okay, understood? That's what allows water and other things like this to flow, right? There's enough connection there that it will start to flow. And then what happens if we start heating up our water? Right? If we start heating up our water, what happens to these molecules?
Start to separate.
They start to vibrate, they start to move, and what happens when we get enough movement? It breaks, right? It breaks. And so that hydrogen bond goes away. And so now we've got gas particles that can float individually. Okay? So that heat just has to be enough to break the intermolecular force to go from solid to liquid, and then we add more heat to break intermolecular forces again to go liquid to gas. Okay? All right, very good. Let's see here. This whole phenomenon kind of hydrogen bonding causes hydrogen-containing molecules to have pretty high boiling points. Okay, high boiling points. Okay, or higher than those not containing hydrogen. Okay, because hydrogen bonding is the strongest type of intermolecular force. Okay, so it causes a higher boiling point. Called van der Waals forces. They're also called dipole or London dispersion forces. I don't expect you to know or have all of those necessarily memorized. I'm just knowing that on your CK12 you're going to see all three of those names. So I want to give you all three of them at one time. Okay? These are the weakest type. So I would go ahead and put that in your notes as well, that these are the weakest type of intermolecular force. They're weak and they're like instantaneous. Okay, what does it mean when I say instantaneous? They're very fast. They come and go very quickly, right? They're instantaneous, so they come and go very, very quickly. So the reason they come and go really quickly is that they are an attraction that results from the motion of electrons within a bond that causes instantaneous dipoles. So I'm going to break that down, but I want to give you a second to write it out first, and then we will break it down a little bit further. All right, so we need to first remember, what does that term dipole mean? What's dipole mean? That's right, it's got two poles, right? It's got two poles. It's got a positive and a negative side of the molecule, right? Di means what? Two, and poles means it's got specific ends, okay? So that's not really what it means, but for us, that's what it means, a positive and a negative side. So dipole means I've got an end that's positive and an end that's negative, right? That's what I do when I draw my polarity dipole moment. I'm showing the positive end and negative end. So when electrons move within the bond itself, it creates what's called instantaneous dipoles. So let's say we have electrons here in this bond, and they sit just like where they're supposed to, nice and shared. But we know that carbon's more electronegative, right? So it's going to pull them a little closer to carbon, which creates a dipole that looks like this. Partial positive, partial negative. Agreed? Right? In a perfectly polar covalent bond, it would look just like this. But what happens if during the motion of these electrons, right, they never stop moving. So what if in the movement of these electrons, they accidentally flip-flop to hydrogen side? Now hydrogen becomes a partial negative and carbon becomes a partial positive. Right? But that would only happen for an instant. Right? The motion of these electrons can cause that change. And when we've got a partial negative, partial positive, right, those molecules might attract for just a second. But when these electrons move back and fix itself, this becomes negative again, this becomes positive. Now those molecules will repel once again. Does that kind of make sense? It happens very quickly and it's very weak. Okay? But that's what we mean when we say an instantaneous dipole. It only happens for an instant, and it's just due to that motion of those electrons and where they're placed within that bond. Okay? So it doesn't happen, it doesn't happen for very long, but it does happen all the time. So they're very, very weak. They only occur for short periods, and they happen in all atoms and all molecules. So these are the only types of intermolecular force that happen in every type of molecule. Okay? Especially in non-polar molecules and noble gases. Okay? Because in non-polar molecules, we don't have dipoles that cause that other type of intermolecular force. All right, so they happen in all molecules, but they are by far the weakest type. Ionic compounds. Remind me, what type of atoms are contained in an ionic bond or an ionic compound? A metal and a nonmetal. Very good. Okay, they are made of a metal and a nonmetal. Or another way you could say it is a cation and an anion. That's the other way you could say it, right? Same types of things. Because what type of charge do cations have? Right? They're there you go, Evan. They're positive. Okay, very nice, very nice. Okay, cations are positive, anions are negative, and they form that ionic bond. Okay. We showed this, oh man, a typo. We showed this transfer earlier when we first started talking about types of bonds, but I'm going to walk through it one more time, okay? All right, let's go all the way back here. Tell me, how many valence electrons does sodium have?
1 or 2.
What group is it in? Sodium's in group 1, which means it has 1 valence electron. Chlorine is in group 7 or 17, so how many valence electrons does it have? 7. Okay, so let's think. How many electrons do we want? 8. So is it easier for sodium to gather 7 or give away 1? It wants to give away 1. And chlorine, is it easier for it to give away 7 or gather 1? Okay, so very good. Sodium wants to give away its electron. Chlorine's like, yep, I'll take it. Okay, so when that happens, sodium gives it away, leaving sodium with what type of a charge? Sodium is supposed to have 11 electrons, but if it gives away 1, now it looks like neon, right? It only has 10. So if it's supposed to have 11, only has 10, what's my charge? Positive, right? I'm short an electron, right? I gave it away. Now chlorine took that electron. It was only supposed to have 17, but it took in 1 more, which means it now has 18. So what's its charge? Negative. And what happens to a positive and a negative? They attract, right? And so ionic bonds, not a sharing of electrons, but a trading of electrons, or a give and take, okay? And so when we do that give and take, we form a full formal charge here, right? They actually gave the electron away. We're not sharing and participating in that. We're actually giving and taking. And so sodium's got a positive, chlorine's got a negative, and they just, get to sit right next to each other. So happy, okay? What happens if another sodium atom comes along? Would it sit on top of it like this? Knowing that this is positive and this is negative, would it sit just like this? Positive, positive, negative, negative? No, how would it sit? Any ideas?
Would it be flipped?
Would it sit like this? NaCl, right? Would it turn itself around so that this positive of this sodium could attract to this negative and this negative could attract to this positive? Yes, right? That's how ionic compounds orient themselves, okay? So that slides right into our next thing. They form what is called a crystal lattice. Crystal lattice. Do you know what the word lattice means? You guys have out under your decks, probably. You know what lattice fencing is? Is that crisscross fencing that sits underneath your deck? You know what I'm talking about? Yeah? That's called lattice. And that's exactly what happens here. It's a grid. Okay? So they get fixed into these grid formats. Okay? It is an orderly arrangement of ionic bonded atoms. Okay? They situate themselves so that they can be positive, negative, positive, negative, positive, negative, whatever. Keep going. Okay? It wants to be in that situation, right? It doesn't want to be uncomfortable. So it will orient itself so that it's constantly positive, negative. Okay? It does it so that the attractive and repulsive forces keep the atoms together. So this one that's shown down here is sodium chloride again. Sodium is the purple, so this is positive, negative, positive, negative, negative, positive, negative, positive. You see how all of these are fitting together? You don't even really know where one compound starts and the next one begins, right? It could be these two, or it could be these two, or it could be these two. It could be any situation, but as long as they're fitting in that grid, it doesn't really matter which sodium was bonded to that chlorine first, right? They're in this grid, and then as we start to break those bonds down, it'll form individual little molecules, okay? But we said for salt, or if you looked in your book, your salt boiling point was extremely high. So it's not going to happen. Okay. Questions with that? All right, this next slide here, I don't need you to write it down. I want to touch on a couple things we've talked about so far, okay? The difference between ionic compounds and covalent compounds. So covalent compounds usually have what types of atoms in them? Metals or nonmetals? This is an easy one. Covalent compounds usually have metals or nonmetals? Non-metals, okay? Non-metals, they share electrons. Ionic compounds are between a metal and a nonmetal, and they trade electrons. This is all review stuff. I don't think you have to write this down, so you can if you want, but you don't need to, okay? Forces between two covalent molecules are not as strong as forces that hold together ionic molecules. Usually we see that in boiling points and melting points. Okay, and most covalent molecules are gases at room temperature. Okay, whereas let's think salt, not a gas at room temperature, right? NaCl is an ionic compound, it's a solid at room temperature. Covalent compounds like CO2, right? Those are usually gas at room temperature. It doesn't work for all of them. Water, right, is covalent and it's liquid at room temperature. Okay, so it doesn't work for all of them, but for the most part, we see covalent compounds have a lower melting and boiling point than ionic compounds. And most of our covalent compounds are already gases at room temperature. Okay, so I want to write out kind of like a strength chart here of all of our types of charges we've talked about so far. Okay, the very strongest type is a covalent bond. Okay, so I'm going to list them strongest to weakest here. And this is, I think, something you should maybe have down. Okay, so the strongest type of bond we see would be a non-polar covalent bond. Okay, what do you think would be a teeny bit weaker than that? A polar covalent bond. Then a teeny bit weaker than that is ionic bonds. Then below that becomes hydrogen bonding. And below that becomes van der Waals. Okay, these two are both intermolecular forces. Okay, so we see the absolute strongest thing are the things that hold the atoms together. And then we see intermolecular forces. Okay, so we go strongest down to weakest there. The top property of metal that we really think about is that they are good conductors of heat and electricity. Okay, they are good conductors of heat and electricity. Can you list some other properties of metals that we talked about a long time ago? They're malleable. Good. What else? Ductile. Good. What else? Yep. Shiny. And they have luster. Very good. High tensile strength, which means they don't shatter. All those types of things are properties of metals. But the important one is that they're conductors of heat and electricity. This is due to the fact that they have they have really highly mobile electrons. Okay, and there's a lot of stuff that goes behind the scenes here as to why that's the case. But a simple way to put it is that your metals kind of have empty outer shells. All right, a lot of metals have empty outer shells, particularly if you're in group 1 and group 2 metals. Okay, because they've got p and d orbitals and potentially f orbitals available to them. Okay, you don't have to know a lot about why that is, but we understand the orbital system, right? So we know what d orbitals are, p orbitals are, all that kind of stuff. So they've got empty outer shells. What I want you to write down for these mobile electrons are called delocalized. Delocalized electrons. And these are only present in metallic bonding. Okay? Delocalized electrons. Break down that word and see if you have an idea what that means.
They're not where they're supposed to be.
Okay, good. Not where they're supposed to be. Or even more specific than that, they're not, okay, kind of, not stable, not idle, good. They're not in one place. There we go. Okay, to be localized means I have really one location I'm at. But to be delocalized means I'm mobile, okay? So delocalized electrons means in metallic bonding, our metals have the opportunity to move and kind of flow, and so that's where you'll see the heat and electricity flow through there. So I'm going to show you just a quick picture of what that looks like. Okay, if my electrons were attached, right, this is a really simplistic picture, but if they were attached, that's what they look like. But when they're delocalized, they have the ability to roam a little bit, okay, and that allows heat and electricity to flow through there. Okay, we're not going to talk a lot about metallic bonding, but I do want you to understand or know that term, delocalized electrons. Okay, it means just they don't have a home.